Hello children, welcome to my class. In this class, we will learn motion of class 9th. Children, observe this animation. The bird is flying. The bird is flying. Next, you observe this house. The house is at rest. Here also, observe this tree. The tree is at rest. Next, observe this car. The car is moving. The car is moving. If you observe all these things, the house is at rest and the tree is at rest. How can you say the house is at rest and the tree is at rest? When the position of an object with respect to other object around it does not change. Observe this one. This is the tree and this is the house. Okay, the position of the object is not changing with respect to time, with respect to the surrounding objects. So then we say that the house and the tree are at rest. Observe this animation, children. The car is moving on the road. See this one. The trees are moving back. The trees are moving back. So with respect to the observer, the position of the trees is changing. The position of the trees is changing. So if the position of an object changes with respect to time, then we say that the object is in motion. The object is in motion. See this one. The bird. This is the initial position of the bird. After some time, the bird reached this position. There is a change in the position with respect to time. So then we say that the bird is in motion. The bird is in motion. If you observe this house, is the house really in motion? Is it really in motion? Or is it really at rest? So it depends on the position of the observer. Position of the observer. With respect to the observer. For example, if the house and all the rocks and building is observed from the outer space by an astronaut, he feels that everything is moving. Everything is moving. So motion and rest are relative terms. Are relative terms. It depends on the observer. Let us define rest and motion. What is rest and what is motion? See this one. The house is at rest. The house is at rest and the tree is at rest. Observe this one. This tree is also at rest. Why? We can say the object is at rest if the position of the body do not change with respect to time. The body is said to be at rest. The body is said to be at rest. Are you clear about that one? So with respect to the surroundings, if the position of the body, if the position of an object or the body does not change, then we say that the body is at rest or the object is at rest. Now see this one. Observe this one. The initial position of the boy is at A. After some time, the boy reached this point B. Okay, there is a change in the position of the body with respect to the time. So if the position of the body changes with respect to time, the body is said to be in motion. The body is said to be in motion. So with respect to the surrounding objects, if the position of the object changes, then we say that the body or the object is in motion. Motion and rest are relative terms. They depend on the observer. They depend on the observer. Motion and rest are relative terms and they depend on the observer. For example, the house is at rest. Actually, is it at rest? Are the students, those who are sitting in the classroom, are at rest? No, they are also moving. When the astronaut observes from the outer space, everything, he feels everything is moving. Okay, because the earth is revolving. The earth is revolving. Are you clear about that one? So with this we can say that motion and rest are relative terms. They depend on the observer. Before going to discuss what is motion and types of motions, it is better to discuss what are the physical quantities, various physical quantities we use in this chapter. What is a physical quantity? All those quantities which can be measured are called physical quantities. All those quantities which can be measured are called physical quantities. For example, length, mass, time, temperature, distance, speed, and time. These are all the few examples for physical quantities. Physical quantities are further classified into scalar quantities and vector quantities. Scalar quantities and vector quantities. See, what are scalar quantities? What are scalar quantities? Those physical quantities which can be completely described by magnitude alone. By magnitude alone, they are represented by A comma capital A comma capital B. For example, length, mass, and time. For example, you take the case of this pen. If you want to measure the length of this pen, see this one. If you want to measure the length of this pen, see, however you measure the length along this direction or along this direction, along this direction, the length is same. The length is same. Are you clear about that one? So it need only magnitude for its description. Such quantities are known as what we call them scalar quantities. So those physical quantities which can be completely described by magnitude, completely described by magnitude. See this one, completely described by magnitude alone. Okay, there is no need of the direction. However you measure, okay, in which direction, whatever the direction may be, you can measure like this or like this. However you measure the length of the pen, okay, so its length is same. So it has only magnitude, no need of direction. So those quantities are known as what we call them scalar quantities. Example for scalar quantities are length, mass, and time. What are they? Length, mass, and time. These are the few examples. Okay. Next, distance is a scalar quantity. Next, speed is a scalar quantity. So many other quantities are there. We will discuss one by one in detail. Children, you observe this one. A boy is trying to open the door. He is trying to open the door. If he want to open the door, what he has to do? He has to apply some force. He has to apply some force. Okay, if he want to open or close, so in which direction he has to apply the force? The direction is very, very important. Are you clear about that one? In which direction the force is applied to open the door, that is very, very important. So those physical quantities which needs magnitude and direction both for their complete description, to describe the physical quantity completely, they need direction and magnitude. Those quantities are known as what we call them? What we call them? Vector quantities. What we call them? Vector quantities. So a vector quantity is one which has both magnitude and direction. Okay, example for vector quantities: force. Force is a vector quantity, and displacement is a vector quantity, and velocity is a vector quantity. Are you clear about that one? So what are vector quantities? Physical quantities which needs magnitude and direction for their complete description. Generally, vector is denoted by capital letter with a directed arrow. Directed arrow. Are you clear about that one? Children, you observe this animation. See, the boy started, a pizza boy started from the position A, okay, and he want to reach the position C, okay. So he started from A and reached B. After that, from B to C, he moved to deliver his pizza. To deliver his pizza. Are you clear? So let us imagine this is 4 meters and this is 3 meters. This is 4 meters. Let us imagine the distance between A to B is how much? 4 meters. This is 4 meters, and this distance from B to his house, that is 3 meters. Okay. So the total length of the path, that is AB plus BH. AB plus BH. How much? 4 meters plus 3 meters. The total length of the path is known as what we call it distance. How much here? AB plus BH, it is equal to 4 meters plus 3 meters, 7 meters. So the total distance, that is total length of the path traveled by a body, is called what we call it distance. It's called distance. The units of distance, SI units, are meters. The smaller distances are measured in centimeters, and still smaller millimeters and meters. Okay, and kilometers. Longer distances are measured in kilometers. So the SI unit is, what is the SI unit of distance? Meters. So how can we define distance? Total length of the path traveled by a body, It is a scalar quantity. No need of direction for its description. It has only magnitude. Children, observe this animation. This is the pizza house. The boy started, okay, the pizza boy started from the pizza house at the point A, and he want to deliver his pizza at somebody's house at C, located at point C. Are you clear about that one? Now he can move like this also, from A to B and B to C. Observe this one. He can move from A to B and B to C. But A to C is the shortest distance. Okay. So the shortest distance from initial to final position, of a body or of an object is known as what we call it displacement. After some time, observe this animation. After some time, the boy returned to again the pizza house. Now at this point, see this one. The boy started from A and reached C, and again he came back to A. Okay. At this time, the displacement is 0. Okay. This displacement is defined as the shortest distance from initial to final position is called what we call it displacement. So it is a vector quantity because it has both magnitude and direction. In the diagram, see this one, AC is the displacement. Are you clear about that one? Now if you observe this, see this here, let us assume the distance between A and B is 4 meters. This is 4 meters. Next, here from B to C is 3 meters. It is 3 meters. Now, what is the total distance traveled by this pizza boy? 4 meters plus 3 meters. Altogether, how much? 7 meters. Now, what is the displacement of the pizza boy? The displacement is along this direction. This is the shortest distance. The shortest distance from initial to final position. This A is the initial position and C is the final position where he want to deliver his pizza. Okay. So, what is the shortest distance here? That is, apply the Pythagoras theorem here, that is 4 meter, that is square root of, see this one here I am writing, see this, 4 square is 16 plus 3 square is 9. I applied Pythagoras theorem. Square in a right angle, this is the right angle triangle. Observe this one. This is the right angle triangle. This is the hypotenuse. The square and the hypotenuse is equal to sum of the squares on the remaining two sides. That is AC square is equal to AB square plus BC square. 16 plus 9 is how much? 25. How much you got? 25. This is 25. What is the square root of 25? Square root of 25 is how much? It is 5. 5 meters. The displacement of the pizza boy is 5 meters. It is along the direction AC. Are you clear about that one? While writing displacement, what you have to do, you have to mention the direction also. So the shortest distance from initial to final position is called displacement. Okay, it is a vector quantity. In the diagram, AC is the displacement. But here when you are asked to find the distance means, what is the distance? 4 meters plus 3 meters, 7 meters. Observe this one. 5 meters is smaller than this 7 meters. Are you clear? So the shortest distance from initial to final position is known as what we call it, displacement. It is a vector quantity. The units are meters. Remember that distance, the units of distance SI units are meters. For displacement also it is meters. But distance is a scalar, displacement is a vector. Summarize what we learnt. Distance is the total length of the path traveled by a body. The SI units are meters. It is a scalar quantity. Distance never be zero. Shortest distance from initial to final position is displacement. SI units are meters. It is a vector quantity. Displacement may be zero. Thank you, children. I hope I made the concept crystal clear to you. Do subscribe and support my channel. If you have any doubt, please post your doubts to my WhatsApp number. Thank you.